Hi everyone. Today, Daniel Ketover is going to speak about the Smale Conjecture in RPG. Please.
Thank you very much for inviting me. It's a real pleasure to be back at Princeton. So today I'm going to talk about objects which are a priori sort of quite complicated. So I'm going to be talking about diffeomorphism group of a closed manifold. So this a priori is quite complicated, but it was proven in the 60s by Palais that in spite of this, it's actually homotopy equivalent to a CW complex. So it's not a crazy wild space. It's the type of space that's considered in Hatcher's book. And so well, here M is just some random manifold. If we put a metric on it, then we can consider a nice subgroup of diffeomorphisms, which is the isometry group, right, which sits right inside of the space of all diffeomorphisms. And so this is infinite dimensional, this guy, but the isometry group for any metric is always a finite dimensional Lie group. Okay, so you could not expect this to be a homeomorphism, but optimistically, so the basic question is if the metric that you put on the manifold, so if the metric G on M has, let's say, well, maximal symmetry, then what you could hope, then this map I, this injection is actually a homotopy equivalence. Equivalence. Okay, so that's the question. To what extent this infinite dimensional space retracts to a finite dimensional space sitting inside of it? Okay, so that's what we're going to talk about today. Okay, so maybe let me just mention some examples. So the first example is just if I take M just to be the circle.
Sorry, what is an homotopy equivalence?
Sorry?
What is the homotopy equivalence?
Sorry?
The definition of homotopy.
Well, you have a map in and a map back, which is homotopic to the identity. And then backwards, yeah. So right, so
Why do you expect this for a maximal symmetry?
Sorry?
Just for a maximal symmetry.
Exactly, assuming we have maximal symmetry for our so you'll see in the examples sort of how it works, right? Because generically, there's no isometry group. There are no isometries. You pick a random metric. But the hope is that if we pick a nice metric, that there's enough links between geometry and topology that we'll get a retraction. So the simplest example is just S1. So the isometry group there is just a O2, right, of rotations sitting inside the diffeomorphism group of S1. Okay, so one way to think about this, just imagine you have a diffeomorphism of S1 which fixes one point as a sort of first case, right? So here's 2 pi, here's 2 pi. Say it fixes some point. Well, then you could think of it as just some sort of increasing function. And so if you could come up with a way to, if I have any k-parameter family of, you can come up with a way to retract that just to the identity function. So this case is you could show by elementary means that there's a retraction of diffeomorphisms onto rotations. So that's the simple case. And then the second case is M is equal to S2. And yeah.
2 by 2 pi. What are they?
Well, I'm just thinking of the circle as a interval from mapping the circle to the circle. That's a diffeomorphism. So say it fixes this point here, which is this point here. Well, then what is a diffeomorphism? It's just an increasing function. It's just a way of reparametrizing. And you can convince yourself that if I have that space of increasing functions, you could write down a formula that will retract it to just the to the identity. Okay. So that one is fairly elementary. This one is actually quite hard. This is about diffeomorphisms into S2, and this was proved by Smale in 1959. And it's already not a trivial argument. So it uses dynamical systems. Okay, so this map I is a homotopy equivalence.
Are there other ways to do it without dynamical systems?
Well, you can now do it with mean curvature flow. So I'll explain in a second actually how that works. But there is another proof using mean curvature flow. Yeah. Okay, and so in this paper in the 50s, he conjectured that the same thing should be true for S3. Okay, this is a famous conjecture. This is so-called the Smale conjecture. And so he conjectured that the inclusion of isometries into the diffeomorphisms of S3 is a homotopy equivalence. Okay, and this was proved by Hatcher in 1983. And this argument of Hatcher is extremely complicated. If you open up the paper, he has to do this retraction, and it's just extremely complicated using elementary means, but very few people, I would say, understand the kind of argument that well.
I guess the obvious question is higher spheres now. Does anybody know anything about higher spheres?
So in S4, it's false.
Right.
I think that's no. Yeah.
Right.
But from the time that so let's just say right. M is equal to S4. That was only shown pretty recently, I think.
We showed that?
I think it was Wana, a Japanese mathematician. Showed this, yeah. Okay. So from the time that this work appeared of Hatcher, it was a question whether you could use geometric means to retract diffeomorphisms down to isometries. So this is a question that really goes back to Yao, which is, is there a geometric proof? Of this Smale conjecture for S3, and his idea, we're going to get to this in a second, but so the Smale conjecture for S3 turns out to be equivalent to the following statement, that the space of embeddings of S2 inside of S2 cross R, and here I mean non-trivial, I'll put a star for non-trivial, that this space is contractible. So we'll see what diffeomorphisms have to do with embeddings of surfaces, but the picture is the following. So what Yao's idea was to put a metric on S2 cross R like this. And so there's a minimal sphere here. And this is actually the only minimal sphere in this manifold. And so if you have some non-trivial, so something which is homologous to that guy, then you could use the mean curvature flow to hopefully retract, this whole family down to one sphere. Okay, so this was the approach, what Yao proposed, but so far it hasn't been done. And if you could do this, then the Smale conjecture for RP3, which I'm going to talk about, would sort of follow if you put some antipodal symmetry here. Then you'd be flowing RP2s down to an RP2.
Just one question.
Yeah.
This equivalence is proven. What is not proven is the fact that that space is contracted.
Exactly. Yeah, so the question is, can you use mean curvature flow to do the retraction? So recently, the so-called multiplicity 1 theorem was proved, which was a big result in mean curvature flow, which means that probably if somebody can sit down and write 200 pages, they could do this retraction now using a flow method.
What is you most likely you said it, but I missed it. What is the star there?
So I mean spheres which are homologous to this central sphere, not spheres which can shrink down to a point. Okay. Right. So that's what we're going to talk about today. Using not a flow, we're going to use min-max theory to prove the Smale conjecture in a bunch of cases. Okay. So before that, let me just mention some consequences of the Smale conjecture for S3. So it turns out that if you have the Smale conjecture for S3, it implies the analog of the Smale conjecture for a bunch of other manifolds, which you could sort of chop up and reduce to the case of S3. Okay, so I won't say the full statement, but we need the following. So this is for Haken manifolds. Let me not even define it. It just means that there's an incompressible surface in the manifold. So here's two examples. So if I take M to be just T2, or really any surface across the interval, and I look at the diffeom, or I take M to be a handle body, right? So just the neighborhood of a graph, something like that. Then the diffeomorphisms of these spaces are retractable, fixing the boundary. So for both of these spaces, the diffeomorphisms of M, which fix the boundary pointwise, is contractible. Okay, so any diffeomorphism, if I give you some sphere of diffeomorphisms, there's a retraction down to one. Okay, and this was proved by, again, by Hatcher and by Ivanov. Okay, so we're going to need that later. Basically, what you do is you chop the handle body with a bunch of discs, and then you reduce it to the case of the Smale conjecture for just 3 balls, which is equivalent to the Smale conjecture for S3.
Did you say that Hatcher used mean curvature or not?
No, he used all by hand. Yeah, there was no mean curvature flow in Hatcher's argument.
So is it difficult to prove the contractibility if you have S1s everywhere?
Sorry, if you have S1s.
So what you're drawing is really embedding of S1 into S1 cross R, right?
You mean this one here? Yeah.
So is contractibility still difficult to prove for S1?
That's a good question. So we know mean curvature flow for surfaces, it exists for all time and has to end at something at a minimal surface or a point. And so yes, you could use mean curvature flow in 2 dimensions for curves and get a proof using geometry for that case.
Because like the circle, you can parameterize the curve and then just,
But you have to do it in high parameter families. And they're not graphs, right?
they're not
graphs, they're embedded, but-
wiggles, yes, but it's still like for S1, you still have a parameterization on parameter. And
Yeah. Well,
but can't you do the same for S2? I'm just.
If you can do it, it will be a great. Well, the problem is, there are saddle points, right? So a minimal disk can have all sorts of weird critical points, and when you have high parameter families, there's like surf theory, which tells you how the critical points change in family. It's very complicated.
This symmetry is.
You have to do it continuously in a family, yeah, and that's what makes it hard. Hatcher uses something called disks with tongues to parameterize things, and I have no idea. Looking at the paper many times, I have no idea what he's talking about. I've stared at the pictures in the paper for long periods, but that's my failing. Okay, other questions? All right, so I want to talk about today other manifolds. So we're going to talk about 3 manifolds. So I'm just going to focus on 3 manifolds with a constant sectional curvature. So K is equal to plus or minus 1, and kind of explain what's known. So the first, so the conjecture is again the same thing as before, right? Is the inclusion of the isometry group of M into the diffeomorphism group a homotopy equivalence. And so the first result is due to Gabai. And so he handled the case when K is -1. So for hyperbolic manifolds, he was able to do the contraction. And now for spherical, for the other spherical space forms, so this is this is right H3 mod some group. And so for spherical space forms, there was a bunch of work. So it was known for lens spaces that are not equal to RP3. So somehow that the RP3 is kind of the RP3 is most similar to S3. I'll explain in a second. And it was also known for the ones that contain if they contain a Klein bottle. This is some geometrically incompressible Klein bottle, and it somehow allows you to reduce to this Haken case. I won't say much about it. And this was done by a bunch of authors, Rubinstein, and others. Okay. Okay, and then in 2018, Baumler and Kleiner, so they used Ricci flow to contract the space of metrics to constant curvature metrics. So they proved so they used Ricci flow. They have to, of course, deal with surgeries and high parameter families to prove the Smale conjecture for all spaces, except for the sort of 2 hardest S3, except S3 and RP3. they're most similar. So they proved it assuming those, and then later in 2019, they proved the Smale conjecture for these two guys. So, it uses all the Perelman's work, and it uses Ricci flow with surgeries. You have to know that the flow is unique through singularities, and so it's a very involved process. But I'm not a Ricci flow person, I'm a minimal surface person. And so it has always been a question whether you can use minimal surfaces to obtain the same result. So the theorem I want to talk about is with Yevgeny Liokumovich. So we prove the Smale conjecture for RP3 and all lens spaces, okay, using minimal surfaces. Minimal surfaces, you should think retracted diffeomorphisms down to isometries. Isometries are like canonical diffeomorphisms, and minimal surfaces you should think are like canonical submanifolds inside of a manifold. Okay, any questions?
Does this include the three sphere or not?
We don't know, not this three sphere. Yeah, so we in several places we use the Smale conjecture for the three sphere. And so this argument we're going to present in theory could work for all manifolds if we knew more about the space of minimal surfaces inside of them. So there's some natural things you would conjecture about minimal surfaces given this. Okay, so let me just explain a little bit about the geometry of RP3. So I'm not going to focus on lens spaces. I'm just going to focus on the one that's the most interesting for us. Okay, so what is RP3? Well, RP3, right, it's just S3 mod Z mod 2. And the way to think about it, right, the quotient, right, so if we consider this to be the projection, the quotient is just a 3-ball, something like this. And so suppose I have a minimal torus. Okay, so suppose T is a minimal torus inside of RP3. So what that looks like, it's going to look something like this. So I'm thinking of this is a fundamental domain of this action. So this is like B3 with antipodal points identified. And so this cylinder actually, because this point is identified with that, it gives rise to a torus inside of RP3. So suppose I have a minimal torus. Well, so let's see if we can understand what that has to be. Well, I could take my torus, right, and lift it up to S3 to see what we get. So the lift of this torus is a minimal torus in S3. Okay, I should say, sorry, I'm only focusing on embedded tori, and those have been classified recently by Brendel. So Brendel showed, he classified all minimal embedded tori in the 3-sphere, and they have to be these Clifford tori. Okay, so what Brendel proved is that the pullback of this torus is a Clifford torus. Okay, so in particular, we know that the area of this Clifford torus is actually, well, the area of the Clifford torus in S3 is 2 pi squared. So this is just 1/2 of it. So this is just equal to pi squared. And the index, if you compute the Morse index of this torus, it's actually equal to 1. So the Clifford torus in S3, if you've studied it, it has index 5. But when you go mod Z mod 2, then this guy only has index 1. Okay, what else can we say about it? Right, and so it has another nice property that it actually looks exactly like that. So if you take RP3 and subtract the Clifford torus, then what you see is 2 genus 1 handle bodies. So this is the handle body, 2 genus 1 handle bodies, which are kind of joined together at the torus in the middle. So these guys are genus 1 handle bodies. So it's clear that this guy is a handle body, but if you can convince yourself that the complement, if you were to enlarge this in this direction, you would collapse to a one-dimensional spine, which is a circle like that. So it's actually so this is true. This is called being a Haggard surface. If you divide the manifold into two handle bodies. Okay, and so the space of, so I'll denote by tau sub t, this is the space of Clifford tori. Okay, this, it's just an algebraic computation, it's just RP2 cross RP2. So there's a lot of Clifford tories. You could take that guy and rotate it around and so forth. Okay. Okay. So that's what I want to say about the geometry of RP3.
Like RP2 times RP2 coincides with the isometry of RP3.
Right. Yeah, you will see. Yeah. Okay. Right. So the Smale conjecture is something about embeddings, and now this is something about we want to relate diffeomorphisms to embeddings. Question is, what is the relationship? Okay, so let's just fix some Clifford torus inside of my RP3. So let's say C. I'll denote it by C for Clifford. This is just the torus inside of RP3. Okay, which is a Clifford torus. Okay, and so the point is that you could project the space of all diffeomorphisms of RP3 onto the space of these embeddings, of these non-trivial of Haggard embeddings of T2 into RP3. And the way you do this is, like, think of this as being like your reference embedding, and if you have a diffeomorphism of RP3, it will just move this guy around, right? So the way this map is defined, if you give me a diffeomorphism, so I have to give you an embedding. The embedding I'm going to give you, right, is just do the Clifford embedding and then compose with phi. Right, so this is the relation. We project diffeomorphisms onto embeddings. And this here means this means it's a Haggard embedding. In other words, it's unknotted. It bounds a genus 1 handle body on each side. So some basic facts are, this map is pretty nice. So F is a vibration. Sorry, P is a vibration. And so what's the fiber? That's asking, what are all the diffeomorphisms which fix this particular Clifford torus pointwise? Well, if it fixes this guy pointwise, it's some diffeomorphism of each handle body separately, right? So that means that it's given by diffeomorphisms of into here and there. But we know, or I explained that actually that's trivial because the diffeomorphisms of a handle body. That's why I mentioned this thing about the Hawken manifolds. That's trivial. So the fiber is contractible. And that means we actually have a homotopy equivalence. Okay, so that tells us this map P is a homotopy equivalence. Okay, so if you're interested in diffeomorphisms, as we are, then it's enough to study embeddings of tori. And sitting inside of this space are the isometries of RP3. And they act very nicely. In fact, they preserve a nice subset here, which is the space of Clifford tori inside of the space of all embeddings. So maybe I'll denote this space here by tau, and it has this nice subspace, which is the space of Clifford embeddings. And so the point is that the Smale conjecture for RP3 is equivalent to the fact that I have a retraction from embeddings onto the space of Clifford embeddings. So if you like, pi k of the space of all Clifford of all Haggard tori retracts onto the space of all of all Clifford tori. So this is supposed to be contractible for all k is equal to 0, 1, 2, 3, etc. So this is just a. So this is just a Whitehead's theorem that if you want to show something retracts, a CW complex retracts to another, it suffices to show that the relative homotopy groups are all zero. Okay, any questions? So this is what I'm going to prove. So the theorem that I want to, or the form we're going to prove it is of this form. So we're going to prove that the space of tori, Hagar tori, relative to the space of Clifford tori is contractible. This is what I want to talk about. Okay, so far this has all been topology and some geometry in RP3. So where is the analysis, right? This is supposed to be an analysis seminar. I haven't really mentioned much analysis. So for that, we need, what we're going to use is a so-called min-max theorem. Okay, so what is the setup? Well, we have to deal with high parameter families of tori. So the setup is going to be the following. So suppose I have a family of, say I have a family of surfaces that's parametrized by just a box, some n-dimensional box. So this is the family of genus G surfaces. Okay, and they're varying smoothly. But maybe as you go to the boundary of this box, one of your surfaces sort of degenerates into something like a one-dimensional set. Like if you shrink that torus down to the core, you can contract it down to a circle. So smoothly, okay, but at the boundary, sigma tau may degenerate to a curve. Like some sort of one-dimensional set, something like that. Okay, so what you do is you consider the homotopy class of this family. So you fix the boundary of this family and you look at all homotopic families. So let me just say, so this is all homotopic families. Let me not write the definition, all homotopic families, homotopic to the initial family, sigma tau, agreeing at the boundary.
Just to double check.
Yeah.
This tau has nothing to do with the previous tau.
Good, yes, good observation, yes.
Okay,
Different tau, yeah.
just to double check that.
Yeah, good. Well, this is a lowercase tau and that was an uppercase tau.
All right.
So I'm sure you can tell the difference with my handwriting. Okay, so you look at the homotopy class and then you define a sort of min-max width. So this is this number, W sub pi. This is, well, you look at the infemal, you take all sweep outs in the homotopy class, and from each one you take the maximal area. And here we have the two-dimensional area of the surface. This is just some number. This is sort of measuring how small you can make the maximal slice in this large parameter family. And the theorem, due to Simon and Smith, in maybe 1883, is the following. So that if this is non-trivial, so it says that if omega pi is strictly bigger than what you see at the boundary, so then the supremum of T in the boundary of the family, so the area of the initial family. Right. This is like saying if I have a function which is 0 at one point, 0 at another, and I know that in the interior it's bigger than 0, then there has to be a critical point. Okay, so then there exists a. Why don't we make the assumption that the manifold has positive Ricci curvature just to simplify things? Then there exists a embedded minimal surface. Sigma infinity, and some integer, some positive integer, such that the width here is is realized by K times the area of this minimal hypersurface, or this minimal surface. So the surface we're getting kind of realizes this critical value of the area functional, but maybe with a multiplicity. That's the first thing. And then we know that K times the genus of this guy is less than or equal to the original genus of the surface if, sorry, I'm running out of space, if sigma infinity is orientable. And if it's not orientable, then there's a slightly different bound. So this is K over 2 times the genus minus 1 is less than or equal to J. So it's saying if you have a non-trivial family, you can produce a minimal surface with some upper bound on its topological type. So if we start with tori, we cannot get anything with more genus than a torus. So this theorem was proved by Simon Smith in the 80s, and they proved these genus bounds, but without these multiplicities. And a while ago in my thesis, I put in these multiplicities, which is stronger. And the conjecture was that these multiplicities never occur, that K is always equal to 1. So this is like a multiplicity 1 conjecture. So this is the multiplicity 1 conjecture. So a long time ago with Marquez and Neves, we proved that if you have one parameter, so if n is equal to 1, then actually the multiplicity that you get is always equal to 1. And in fact, the limit is not orientable. It is orientable, and sigma infinity is orientable. Okay, and very recently, Shinju and Jisha Wang, they proved that the same thing, but for all possible number of parameters. So they proved that for all n, we have this conclusion: multiplicity is 1, and sigma infinity is orientable. Basically, if it's not orientable, it has to occur with multiplicity 2. So this is a big sort of geometric advance. This was done maybe a year or two ago, maybe I forget, 2023, I think. Okay, any questions?
But it is still true that the genus could be lower in the limit.
Exactly. Yeah. So the genus can drop, and that's a big problem. So let me explain what happened. Let's just see how we are with time. Okay, perfect. So let me give you one concrete example of this theorem, which is going to be relevant, and then I'll start to explain how we prove the Smale conjecture for RP3. Right. So what's an example of this min-max theorem? Let's just take the standard RP3, and let's consider genus 1 sweepouts of it. So I'm going to consider a 1-parameter family, sigma t tau, where tau is just a 1-parameter family, but I'll write it as -1 to 1. And so it's going to start. It's going to start at this sort of one-dimensional line there, which is a circle in RP3. Then it expands to become a Hagar torus, and then it will collapse. It's a bit hard to see if you're not used to the picture, but you can make a 1-parameter family of tori starting at this circle and ending at the circle there, which all have genus 1. So sigma -1 is a circle. Sigma t is a Hagar torus. For t between -1 and 1. And when we collapse to the other side, you're one of these other circles. So this is again a circle. So this is an example of a 1-parameter family. I mentioned that we need to allow them to generate at the boundary. And so here at the boundary of my interval, they're collapsing onto circles. Okay, so we want to apply the min-max theorem, so we have to look at this number, the width. In order to apply it, right, we need that the width of this family is bigger than what's at the boundary. what's at the boundary here is just a circle, so it has 0 length. So it's a fact. So in order to apply the min-max theorem, we just need to know that this width is positive. But this actually just follows from the isoperimetric inequality. Because these tori are sweeping out the entire space, and so it cannot be the case that the area of all of them is arbitrarily small. Okay, so the min-max theorem applies, and we produce a minimal surface. Okay, so we obtain some minimal surface, sigma infinity, which the multiplicity is 1, so we know that the area of sigma infinity, well, actually, sorry, we don't know what the area is, we know that it's equal to the width, is equal to this width. So I told you it can't be non-orientable, so we're in this case, that means it's either a torus or a sphere, but there are no spheres in RP3, there are no minimal spheres in RP3, because if there were, suppose you have a minimal sphere in RP3, you could lift it up to S3, and you would get 2 disjoint minimal S3, S2s there, which doesn't exist. So in fact, this has to be a torus, and by the classification earlier, this has to be a Clifford torus. Okay, and we know, of course, so now we know that this number is also equal to pi squared. And this is, it's realized in a nice foliation, right? The sort of CMC foliation where you have the Clifford torus here and you take CMC tori inside, foliating in and out. Any questions about that? So that's the simple example of this theorem. And this is just one parameter, but of course we need to deal with many parameters, and that's what Smale conjecture is about. So maybe I'll erase this theorem up, since we will use it. So in the last couple of minutes, I could explain the idea. So Smale conjecture for RP3. So we want to show that these relative homotopy groups vanish. Well, that means there has to be at least one which vanish. So let's assume k is the least integer, right? Such that the relative homotopy group of tori relative to the Clifford tori is not intractable. Okay, and that means that I have a non-trivial family. So what does that mean? That means that I have a map F, which you could think of it as going from the disk, the K disk, into the space of all tori, with the property that the boundary of this disk is mapping into the subspace of the Clifford tori. So this is what we have. So I'll draw a picture of the disk. So this is a disk, and we have some decay. And at the boundary, at all these boundary points, we are just seeing Clifford tori at the boundary, but these guys are just general tori. And somehow we want to retract everything to the space of Clifford tori. Now you might, somebody was asking about using a flow. You could try maybe to use mean curvature flow for all of these tori and get down, right? But the problem is maybe some torus in the middle is very, very close to the one-dimensional spine inside of here. Maybe when you do the flow, you just actually go down to 0. And so that won't be a retraction to a minimal torus, that will be a retraction to a curve. Okay, so we need so the first sort of key thing that you have, the first key idea is step 1, is that we extend this map F to be a map from a cylinder. Okay, so we have this extension, I'll call it F star, from dk across the interval into, again, the space of tori. So let me just draw a picture. So we're going to make an extension. And the way we do it so that each line going up and down is a non-trivial one parameter sweep out of RP3. In other words, it's like the CMC foliation that we had over here. So we make this extension with the following properties, right? So that, right. So the T goes from -1. If I look at the one parameter family, so if I take any point inside of here and look at the one parameter family, this has got to be a sweep out, is a Haggard sweep out of RP3. Okay, so we want that. And of course, at the boundary, we had very nice, beautiful geometric Clifford tori with area pi squared. We want them to just be like the standard CMC foliation, right? So it's an optimal foliation, let's call it. So this is true for all x in the disk. But then at the boundary, so for x in the boundary of the disk, we want this family, this one parameter family, to be is an optimal foliation.
So,
Yeah.
so what you're saying here is that you have a way.
Yeah.
that I give you a torus and
Yeah.
you produce for me a one parameter sweep out.
Exactly.
And this is continuous in all possible senses in when I move the torus.
Exactly. Yeah. So I didn't say why this is possible, but if you remember, I erased it, but there was a homotopy equivalence between diffeomorphisms and embeddings. That means if you have a family of embeddings, it corresponds to a family of diffeomorphisms. And you use those diffeomorphisms to have the extension. Okay, so.
Using the S3, the theorem for.
Exactly. So in particular, we're using that the fiber is contractible, and so that the existence of the extension follows from the Smale conjecture for S3, exactly. And that's why if you try to do this proof for S3, you'll run into problems because you need the Smale conjecture for S3 to make it work. And so for those who are old enough to remember the Wilmore conjecture, probably only a few, but the Wilmore conjecture, if you remember, they had these conformal parameters and they had to add an extra parameter in order to make the argument work. And that's sort of what we're doing here. We need to add this Haggard parameter to get something non-trivial. So that's the first step, make this extension. Okay, the second step, step 2, is the min-max theorem. So we have this family, right? And we look at the homotopy class of this family, right? So let omega be the homotopy class of this family, this sweep out F star. And we want to know what the width of it is. So let's call it pi. So to apply the min-max theorem, we need that the width is bigger than what you see at the boundary. So what do you see at the boundary? Well, at the boundary here we have pi squared, and then here this is all decreasing, right, down to 0. So we have pi, the maximum that we ever see, and at the boundary here, these are just one-dimensional graphs. So the area here is 0, and the area here is all 0. So the biggest that we ever see is pi squared. So the min-max theorem says that if the width of this k plus 1 parameter family is bigger than what we see at the boundary, okay, then we get a critical point. But what critical point can we get? Well, again, it's a sweep out of tori, and we can never get a sphere, and we cannot get RP2 with some multiplicity because of this multiplicity 1 theorem. So all you can get is the Clifford torus itself. So that means sigma infinity is the Clifford torus. Okay, but that's a contradiction, right? Because the area of this surface is equal to the width, which is equal to pi squared. But we were assuming that it's bigger. So assuming it's bigger, so this is a contradiction. And that means that the width is not bigger than pi squared. This, the conclusion from this this analysis is that the width is actually equal to pi squared. Cannot be less because it already has pi squared at some points on the boundary. And it cannot be greater because it would produce some minimal surface which doesn't exist inside of RP3. Any questions?
But this does not conclude, or it's obvious from here to conclude? I'm missing something.
No, we're not done.
Okay.
That's just the end of the step. Yeah. So I'll keep this picture. This is just so far. So, right, so what we know is that we can sort of find, well, let me just erase. Right, so since the width is equal to pi squared, that means that so this is the next step, which what do I have to step 3? So we know because the width is equal to pi squared, so it means that there exists a sequence of sweep outs in the homotopy class, in this homotopy class pi. So I'll write it as sigma I x t. So we have a family here that are in this homotopy class, where the maximal area is approaching the width, which is pi squared. Okay, so that's such that the supremum of the area of this guy, x of t, this is over x of t in the entire cylinder, so that's dk cross I. This is less than pi squared plus 1 over I. This just means we can sort of pull them tight. That's the definition. This is what the definition of width is, right? This is just restating the definition that the width is equal to pi squared. Okay, and so what's the idea? So the point is, so everything in this, I have sweep outs, I have these sweep outs where everything is very close to pi squared. But the key idea is that, so if I just restrict my family to one of these yellow lines, that means that this is a 1-parameter family where the maximal area is very close to the optimal thing, which is pi squared. So if you remember, I showed over there, right, that if you just restrict to 1-parameter families, the width is pi squared. So that means, what that means is, if I restrict to each of these lines, there has to be some point on the line which is very, very close to a Clifford torus of some sort. Right, so this is like restricting to each line separately, because we know here that when we do 1-parameter min-max, we have to get the Clifford torus. So let me just stick that. Okay, so right, each 1-parameter family, if I just look at this 1-parameter family where t goes from -1 to 1, is a 1 sweep out with maximal area approaching pi squared. And that means that for large I, if I go really far out in my sequence, there exists for each x, there exists a t, so there exists t sub x, right, such that this guy here, sigma I x, evaluated at that particular t, where I drew that line there, that this guy is close in a weak sense, and this is, so it's close as varifolds to a Clifford torus. So I didn't say that when I stated the min-max theorem, but it also means it also follows that some minimaxing sequence also converges to the Clifford torus. It's not just that there exists a torus; it arises from one of these sequences. Okay, so what's the point? The point is, this is true for each line that I drew. So that means actually what I get is for each line I get something. So what I produce is some sort of relative cycle. Maybe it has topology, it may not be a disk, but I have a relative cycle here where each point here is very close to a Clifford torus. And it has to have the same boundary because we know what things look like at the boundary. This is just the CMC foliation of RP3.
But here, might be delicate or technical, but I'm not sure if it's totally easy. You are claiming that when you move X,
Yeah,
Tx moves somewhat, well, not really continuously, but you can make a choice that is.
exactly, yeah. It's not completely obvious, but it is for, that you could produce a continuous family this way. There may be other components, right? It may be quite complicated, but because we know what the boundary looks like, it forces there to be this relative cycle. Okay, so we get this, so that yellow, I should have used a different color. So what we get is there exists a relative cycle. Let's call it MI. That's the yellow surface with genus there that I drew, that's sitting inside of my parameter space, right, with the boundary of MI just being equal to the same boundary that I had to begin with of my initial family. And so that MI is homologous to the initial family, DK cross 0. This was the initial family that I was trying to retract. Okay, so see how much time do I have? Okay, you go 50 minutes, or how, am I over already, or?
Oh, you're not over. I'd say that you have 5 more minutes.
5 more minutes, yeah, so I don't want to, okay, so what we get is, we were trying to construct a null homotopy, right? I want to take this disk and homotope it to another disk where everything in the interior is a minimal torus. But what we have is sort of a null homology. We have something homologous to it, which is in the space of, which is weakly close to the space of Clifford tori. So in the last couple of minutes, so we have this family, we want to retract it. This is, everything here is very close in a weak sense to a minimal torus. How do we actually do the retraction? I will just draw a picture. Let's assume there's just one minimal torus, right? So let's assume we have some minimal torus here. And we take the tubular neighborhood of that torus, so a small tubular neighborhood. And we know that every torus corresponding to a point here is very close in a weak as varifolds to this central torus. So what we have is some sort of picture where maybe it goes out, but it has very, very small area when it goes out. But it sort of basically looks like it's close as varifolds to this torus. Maybe it wiggles, etc., and maybe it leaves the tubular neighborhood. Okay, so the next step is we need to retract this guy into the tubular neighborhood. Okay, so how do we do that? Well, if you just stare at this picture, there's an obvious way to do the retraction, right? You just pop this disk through here and then pop it again through there. And it turns out that, so there's a Hatcher's argument. Remember, I told you Hatcher had this paper for Hawken manifolds. What it amounts to is like a continuous hair retraction to homotope the family, this MI, so that all the surfaces here are actually contained in the tubular neighborhood of a Clifford torus. This is the key point of the whole proof. If you have two tori in RP3, they can intersect in very complicated ways. And you don't know how to push one through the other. There's no canonical way to do the pushing, right? They could intersect in essential curves, etc. But you see, if you could retract them weakly to the space of minimal tori, then to get it in the tubular neighborhood, you're just really dealing with little disks where there is a canonical way to push. Okay, so this is like the punchline of so we do this to get everything in the tubular neighborhood, and then I wrote it on the board, T2 cross interval, the diffeomorphism group of that is contractible. Once they're in the tubular neighborhood, you could easily retract them to a single torus using Hatcher's theorem, Ivanov for Hawken manifolds. So that's the idea. And then so then you retract it to the torus. We produced a null homology, but there's a very famous theorem in topology called the Hurwitz theorem that says that if the previous homotopy groups vanish and you have a null homology, then it can be you also have a null homotopy. So that's why we had to start with this smallest non-trivial homotopy group. Okay, so a bit rushed at the end, so thank you for your attention and questions.
Is there any question?
Can you do this on other three manifolds?
If we could classify the space of minimal surfaces realizing the Hagar genus or any genus. So we're really using Brendel's result. So like in the Poincare homology sphere that has Hagar genus 2, we conjecture there's only one genus 2 minimal surface up to ambient isometry. If we could do that, then the argument would work. In hyperbolic spaces, I have no idea how to even begin to do it.
At the very beginning, you said, yes, Federico asked, that everything works only if there's a lot of symmetry, and it's pretty clear why, at least the Smale conjecture works only if there's a lot of symmetry.
Right.
But the second part, the reduction to minimal surfaces, like I'm wondering, is there any reason not to expect it to work? Let's say three-dimensional manifold, let's say perturbation of S3 or RP3 as you prefer, and let's say that you take again ergar tori or some simple embeddings, and you say, is it true that all these embeddings are in fact diffeomorphic, well, not diffeomorphic, homotopic to the minimal embeddings? Is this a reasonable guess?
See, it won't be true. So like if you perturb the metric a little bit, instead of having a family RP2 cross RP2 of clifford-tori, you're going to have finitely many.
Oh.
And then you're going to retract it. It's going to be complicated because you have these critical values, which will spread out, and you don't know what it's doing between those two critical values. You could probably argue, but it's very nice to know exactly what they are.
So even the fact that the minimal surfaces are in the right dimension, this is also something that really depends on the symmetry.
Yeah, you need to pick the right metric. You need to pick the round metric, so for it to work. You could try the metrics, but you lose control between the critical values of the.
One more question. So I don't get it, and like you claim that here I'm looking at the yellow picture. You're making the point that this T of X, it can be chosen somewhat continuously.
Right.
I really don't see why it could not be. Like, let's say that we are in dimension K equal to.
Well, this is a smoothly varying family, right?
The yellow thing.
The thing is, we know what is at the boundary. So just think about it, you're building it up from the boundary. The boundary has nowhere else to go. It has to close up somewhere.
Because the boundary is connected.
The boundary is fixed, and connected.
So
it can't like go, you're right. It could sort of stop and then come, but it has nowhere to hit here. Because there are no clifford-tori here. These are all far away from clifford-tori. So that's why you get something homologous to the initial family.
Thank you very much. Is there any other question?
Okay.
Thank you.
Thank you. Thanks.